Good morning, good afternoon, all. My name is Chris Doran. I'm a technical sales specialist here for Global Test Supply. Thank you for joining us for our webinar today, and this is brought to you by Global Test Supply University. Today's topic is electrical power testing with Fluke. We'll be covering a lot of information throughout the presentation over the next 40-45 minutes or so, and we'll have a Q&A period at the end of the presentation. That said, we do encourage you to ask questions at any time, so please use the chat feature or the question feature throughout the presentation. If anything jumps at you while we're covering a slide, please just jot it down in there and we will get to your question at the end of the presentation as mentioned. Global Test Supply and Fluke have been working closely together for many years. We pride ourselves on being a leading distributor of Fluke in the US. This is a result of our dedication to offering you our product expertise, our service, and our competitive pricing. Today's webinar is presented by Ken Reeves. He's from Fluke. Ken is Fluke's territory sales representative based in Alberta, Canada. He has over 31 years of technical test equipment sales, which include over 20 years working directly with and for Fluke. So Ken, I will turn the presentation over to you.
Thank you very much, Chris. Just a quick confirmation everybody can hear me.
Yes, sir.
Awesome. Hello, welcome. My name is Ken, as Chris mentioned, and today I'm going to be presenting to you kind of a high-level overview of power testing and an introduction to it, understanding some of the methods, practices, and solutions. We have some points we'd like to cover off today. I'm not going to read every single one of these, but we're going to understand what is power testing, what is power and energy, what tools can you use today to find that information, what type of power testing equipment is out there, perhaps what categories there are, kind of do an overview of what Fluke products are available, and then go through some best practices to solving problems, employing a bunch of different types of methods, giving you a little bit of background on what is power quality, how do you know you have some problems, and then eventually get ourselves to the end, hopefully about 45 minutes from now, where we'll be able to do a quick wrap up and potentially answer some of your questions. If you have any questions as we go, please use the chat function. Chris will moderate at the end and we will try to do our best to cover them off for you while we're here today. So without any further ado, let's set some real quick terms here. What is power? What is energy? And have a quick discussion about that. So power in an electrical system is the voltage and current available to do work. We call that watts. You're probably all familiar with that term. And to measure power, you need to measure voltage and current simultaneously at the same time. We will talk about it a little bit further in the presentation when you're using some basic test equipment and where there might be limitations there. Energy itself is the rate at which power is produced, or in our case, most likely consumed. And we describe that as kilowatt hours, which is basically the mathematical function of, shown in the graphic above, 1 watt of electrical power over, say, 1,000 hours is 1 kilowatt hour of energy. And as we change the wattage and the time that we're measuring, we're changing the kilowatt hours, and that's just a rate at which we are consuming the energy and how much energy we've used over a period of time. We're all pretty familiar with kilowatt hours, especially if you look at your own electrical bill, and that's the indication of what that is, and that's the terms we're using here so far. So it's getting on the afternoon here, so let's have a discussion around beer. Beer is a good way to, at least this particular drawing is a good way to understand the limitations of the previous discussion I mentioned. So we talked about watts, which is the real power portion, but let's talk about the different factors involved with being able to get us our measurements that we're looking for. So right out of the gate, apparent power is also known as system capacity. What is the ability of the utility to provide us both voltage and current? And it is strictly a multiplication of the two between voltage and current. And as we measure this out, this is what the utility, may be having to provide voltage and current, but in our case, we're looking at watts. So let's draw the kVA as just a red line up and to the right. The watts itself is what is the real power? In other words, what is the work being done? In a beer application, the work is the beer. And in many cases, we can't fill a beer glass full of all of the beer. There's usually some head associated with that beer, and that's what we describe as kVAR. And kVAR is reactive power. You can consider it wasted energy, although it does have a role in making sure that our systems are operating. Basically, that power is used to sustain the electrical system on the capacitance or inductance side of our distribution network, and allow us to, make sure that the real power is delivered. In the power triangle, the kVAR is a vertical angle. And I'm just going to move the slide forward one more. It shows that the graph for power factor, which is a simple way to communicate basically the relationship between kilowatts, kVA, and the kVAR. And the power factor is a single number that's identified between 0 and 1. 1 being unity power, where the glass is full of beer, and 0 being no power, where basically the glass is full of foam. And we're ultimately trying to increase our power factor to the point that we're getting the most amount of power out of our system capacity. And then that's typically what happens. In fact, some utilities will charge penalties associated with creating too much beer when you pour it in, creating too much foam or head on the beer when you pour it in correctly. It's basically a penalty they charge. And those penalties, depending on what region you're in and what the actual penalties are, if they have them or not, are typically anything worse than, say, 0.85 or 0.9, again, depending where you are. And what they're really doing is they're charging you for your inefficiency to pull power down that system, and they are required to deliver you voltage and current, so they need the system capacity. So they're trying to penalize you and recover their costs of the reactive power that is being wasted. Okay. Let's talk quickly about some basic tools to give us these measurements. So in our world, in the Fluke world, we have clamp meters and digital multimeters. For the most part, they both measure voltage. The clamp meter will easily measure current with its clamp. On the digital multimeter, you would need an accessory to plug in your meter and measure current. We sell these accessories are either jaw type accessories or iFlex CTs. The iFlex CT, if you're not familiar with it, is a rope type CT, a Rogowski coil, that allows us to connect through tight connections or over bus bars or odd shaped conductors. And it just makes life a little bit easier. And they're actually really good on the low end of current ranges. Most of the clamp meters and multimeters that you may have in your toolbox already might have the ability to measure frequency. I'll explain why that'll be important here shortly. And most of them, actually all of them, should have the ability to measure resistance. And then from a Fluke Pro tip, which we'll see throughout this presentation, basic tools are good for doing quick checks. So is there power? Do I have voltage? Is there current going to the load? How much is that current? Is it within normal ranges? Is there a fuse blowing? We can use that by measuring voltage or resistance or whatever the case may be, taking the fuse out of service and seeing if the fuse is blowing. So for some very basic tests. The next one on the list there says, is there current on the neutral? So if I'm in a distribution system and I had current on neutrals, you may not expect that to happen, and it's a kind of a phenomenon that happens specifically with triplet harmonics. And having a clamp meter or a multimeter that measures frequency gives us the ability to clip onto the neutral and measure the frequency. And if it's 180, then there's a real good indication that the current being flowing in that neutral is actually caused by single phase non-linear loads. It's kind of a mouthful, but basically loads that aren't drawing the current off resistively or through the whole voltage waveform. They're kind of just sampling and pulling current off in that particular pattern, usually typically at the peak of the voltage, and that creates some harmonic situations that are left to flow through the neutral, which you wouldn't normally expect. But having a basic tool can help you find that out and figure out if you're having issues on that realm as well. So let's do a simple power measurement using a clamp meter. So we would connect our clamp meter over the conductor, and we would measure and record AC voltage. So let's plug our test leads in, measure it, and we would write it down. So write it down on a pad of paper. Measure and record your AC current, and just write it down. I know that this is saying 10.2, it's not 323, which happens to be the model of the clamp. But in our case, we'll just write down a value that we're measuring with our clamp meter, and we multiply the two together, and that gives us VA. So if you remember your beer, VA is the system capacity, in other words, what is actually happening. What doesn't take into account is it doesn't take into account any of the inductive or capacitive loading effects on the system. And the reason for that is that there's usually phase angles associated with that. There may be some other current and harmonic issues associated with that, but we're just getting a general overall health for the VA. This is still a valuable measurement because a lot of equipment is nameplated with what the VA is, and we can reference that. So if we have a motor that's telling us that we have 1250 VA and we connect it up and we're at 1224, then we're well within limits of what that motor is expecting to draw off of our system. Okay, so it's a good way to do some quick checks. I wanted to bring this particular clamp to your attention. It's recently been added to the Fluke line. As customers of Fluke or users of test equipment, I don't expect you to keep on top of everything. This thing's been out for about 18 months now. And what the new clamp meter has done is we've added this little yellow section and a little symbol there for something called Fieldsense. Now, Fieldsense is super cool. When we make a ground connection to the clamp and then measure a single conductor for current, we have the Fieldsense capability to automatically and simultaneously measure voltage on that conductor as well. So we are making a non-contact voltage measurement as well as a current measurement together at the same time. Now, going back to that previous slide, when we have voltage and current, we can multiply them together, and therefore we give you VA. So it's actually really kind of neat to have a clamp that can just quickly, easily connect on. The really interesting thing is that this particular model has the ability to clip on 3 phases of voltage and 3 phases and measure them all simultaneously and automatically calculate some power information for you. So it really does a real quick, easy job of getting us past that first hurdle of saying what's actually happening from a VA perspective. We also have on this particular clamp, and it's not highlighted here super well, but we have this blue Fluke Connects functionality. And I'll talk more about what our wireless technology Fluke Connects is all about in the next couple of slides. Another basic tool for the job that you should consider having if you don't already is a thermal imager. In fact, we've made it easy by making pocket thermal imagers that can just literally fit in your pocket. They make non-contact temperature measurements. They're quick and easy to use, and they're very good at helping you identify potential electrical problems that present themselves as a thermal issue. So those might be load issues, or they might be issues with regards to, the health of the connection itself. Is it becoming a loose connection or a corroded connection where it creates resistance? Current through resistance creates heat, and we will see that using a pocket thermal imager. The pro tip on this is we recommend that you widely deploy these through your maintenance teams. So if you have a thermal imager already locked up in a cabinet and there's usually 1 or 2 people that are allowed to touch it or make thermal scans with it, we recommend that you put a handful of these pocket thermal imagers and deploy them throughout your system. You can use them with the mechanical group, the electrical group, anybody that needs to see temperature. And you can start to capture images while you're out doing your job and potentially use them to identify a problem much earlier than doing, say, for instance, a 6-month or a yearly scan, or when you have a problem and now you need to pull out the thermal imager. So, again, having more frequent and regular samples of what's going on in your various electrical systems will help you identify problems sooner rather than later. Getting back to the concept of Fluke Connect. Fluke Connect was a technology we brought out, I'm going to say about 5 or 6 years ago. And what it is it's kind of a catch-all term for our wireless capability. Imagine we had our multimeters previous to that, and we would show you a value and the technician would be there and read or measure the value while they're in front of their meter. What Fluke Connect allowed us to do is create a little bit of safety and potentially the ability to log and record. So what we have is the ability to communicate wirelessly using Bluetooth to an app on your phone. So now you can leave the tester inside, for instance, a closed electrical cabinet that'll communicate through that cabinet and be able to read it on your phone remotely. So if you have other load changes or other things you want to investigate while the cabinet's closed, you'll be potentially reducing your PPE and be in a safer environment. We also have the ability to turn on logging remotely or trend information, you could actually turn on logging, walk away, come back, reconnect to the device, and download that log data into your phone. And from the phone, it can go to a computer or sent as a text or an email or whatever you want. There's a lot of different functionality and capabilities. This is just a general overview of what we can do with Fluke Connects. And they seem to be model specific in our world. So when you look down the path of picking a piece of test equipment that has FC or Fluke Connects in the part number, take a look and see what functionality it has and how it might be able to, improve your job. You may find that you have a tool, say for instance, a 376 clamp meter, which is a very popular industrial clamp meter that we sell. We came out with an FC version of it. You may have, went to go buy a 376 and provided a 376 FC. That traditionally happens where we just add the functionality to existing products. So it's been out for a few years, and then as we come up with more products, we'll have more and more of this functionality moving forward. Okay, when is a meter, or clamp meter in our case, not enough measurement capability? So beyond basic tests, it becomes more difficult to complete power measurements effectively with a single input tool. And that's really the limiting factor. Either it can measure current or it can measure voltage, but it's difficult to do both at the same time. It also becomes that much more difficult when I start adding phases. So if I have a 3-phase electrical system, that means I have to measure 3 phases for voltage, 3 phases for current, potentially the neutral for both voltage and current, and potentially ground, like the neutral ground measurement, which would be the voltage on the neutral. So that's where we're getting a situation where we have multiple inputs. And doing that with just a clamp meter or a multimeter can be pretty difficult. In addition, basic testers don't account for angles between phases. They don't measure simultaneously, so they're not measuring the voltage and the current simultaneously. So there might be some changes that have happened in the electrical system while you switch and move between those two functions. And they don't, because they don't have the phase angle, they also don't accurately calculate watts or VA or power factor as we described earlier, because all of those measurements are required to know the phase angle, okay? The values are measured again at different times. A long list of other power concerns are missed. So without diving too deeply into what these are, harmonics can be missed with a power class or with a regular clamp meter, trend in values over time, or fast voltage and current events. So when you need to see a wave shape or phase relationships, that's really where you need to kind of consider something beyond just a piece of test equipment. Usually you're looking, when you want to see the wave shape, you're looking for the signal quality. In other words, is it a sine wave? If it isn't a sine wave, what does it look like? Has the sine wave been truncated at the top and bottom? Are there little, glitches along that sine wave that may be an indication of transient issues? How does the phase for voltage and current relate to each other? And can we see where their zero crossing points are and what are the angles? So that's where you need to start considering other tools. Trending over time, multimeters and clamp meters will have min-max average on them. At least some of them do. But what's happening in between those points where it captured a maximum or a minimum value? Many times the maximum is a good indication for, say for instance, startup current on a motor, and having that max value can do that for you. But true trending over time, you usually need to have logged intervals, and that is not typical of a clamp meter. Some of the FC products can do that for you, so we can talk about how that would fit into your system of test equipment and tools in your arsenal to take care of the problems. But again, just keeping in mind that usually that's where we transition from a clamp meter into something else, okay? Some of our high-end multimeters, like the Fluke 87, that is pretty much an industry standard since I started in 1989, has peak capture capability and can capture up to 250 microsecond of peak values. Just take a sip of water here, sorry. The issue there is, what if it's more than, what if the event is happening faster than that? Is there something we're missing? And again, getting back to the first part of the discussion I mentioned where you have multiple inputs for voltage and current and 3-phase systems, all of a sudden you've definitely maxed out what your clamp can do. So in the past, and in some cases even today still, an oscilloscope is the next natural step. And the oscilloscope is actually the basis, or at least the technology is the basis for all of our power quality testing tools. Again, we have two different main families, the 120 series, which has 2 inputs. It's good for single phase. In fact, the 125B actually does power quality measurements built in. So if you have single phase power quality concerns, the 125B would probably be a decent tool to be able to give you the ability to see beyond what a clamp meter is going to do for you. The 190 series is available. It's faster, a little more powerful. The channels are what they call isolated, so the grounds are not connected, which provides some ability to mix and match your inputs. But this gives you the ability to have 2 or 4 channels. Again, it's not practical for 3-phase systems. Having only 4 channels will allow me to see just the voltage or just the currents, or maybe 2 phases, and then that would be it. So it's not really practical, overly practical for 3-phase systems. Although there is a case to be made for having a scope meter work in conjunction with a power quality analyzer for an end-to-end test on, say, variable frequency drives. And we can talk more about that. In fact, give GTS a call if you have any of those types of applications and you'd like to maybe understand how you can use your scope meter a little bit more frequently. Again, from a power testing point of view, the concern is that there's ultimately not enough inputs. So let's take a look and see what we have to help that out. So the takeaway, one of the key takeaways today is 3-phase systems require 3-phase solutions. Fluke offers full 3-phase tools, everything from, we'll get to, entry level to really super fast recorder type products. The 3-phase devices are easy to connect. If you can connect a voltage and current using a clamp meter, then it's just extra connections. You can make the 3 connections for phases and for voltage, and be able to simultaneously and instantly measure voltage, current, frequency, VA, VAR, wattage, power factor as almost a bare minimum in terms of what you're going to be able to do. Okay. Many times there's memory built into these power loggers, and then therefore we have the ability to have up to 400 different measurements calculated and be logged and stored in memory. They almost always have a graphical touchscreen, which allows users the visual feedback for what we're actually measuring and looking at live or trended over time. And if you notice in this picture, the person is using a pair of gloves, and he's definitely in a properly outfitted PPE situation, but the device itself will still run touchscreen using a pair of gloves. You don't need to do anything special. It works just fine that way. So there's some really well thought out ideas that we have when we're developing power quality tools for customers in the field. There's software included with our products on the power quality side, and they're across the full family. So what I mean is if you have a mix of power quality tools, or you bought a power quality logger and you need something else that does more horsepower, the software you're familiar with would be compatible across all the family. The pro tip that's written in the corner, and I'm sorry for the size of it, it's a little small, but basically it suggests that you use your 3-phase tools more frequently. Typically some people spend, 5 to 10,000, whatever the value of their test equipment is, and then they feel that because it's so expensive, we shouldn't be pulling it out. And I would highly recommend that it's the other way around. You've spent a lot of money on it. Find ways, and we'll give you some tips and hints here later, at how to use this tool more frequently. It allows you to become more comfortable with the functionality and navigation. You're going to have the added benefit of buying that tool and maybe potentially find problems ahead of time. And you'll also know how to operate it when you really need to know it, when the chips are down and you need to get power back onto a system, as an example. Okay, in the Fluke world, we've categorized basically 3 different types of power testers. So as a bare minimum entry level, we have tools that we call loggers. Loggers will do the 3-phase connection, allow us to have deep memory. They typically capture values that are half of a second or longer, so 30 cycles or so. And we capture a value for that. We're not going to give you waveform detail. That's a limitation of the logger, but it's intended for 30-day load studies. So if somebody comes to you and says, hey, I'd like to add 100 amps to our distribution system internally, and you go, I'm not sure, it's a 400 amp breaker, and my clamp meter says it's running at 250 amps, I don't know, do I have the room or not? You're probably going to want to log that over a couple of business cycles, at the minimum a week and maybe a full 30 days, and be able to trend that data over time to make sure that you have enough headroom in your distribution system that what you add is not going to trip you in the future. If you have some billing analysis questions, you get a utility bill and it doesn't make sense, having that logged data to be able to compare will help you get a better handle on your energy situation, energy consumption, that is. We have some tips and hints later on the presentation about how to do that. Nuisance tripping, if you have something that's tripping and you don't know why, having a logger available will be able to allow you to trend what's actually happening when that trips, or maybe potentially before it trips, so that you can get a handle on, you know, what the potential problem is if that load happens to energize while something else is happening. And again, power analysis because of dynamic load changes. So, you know, there's very few situations where the load is consistent all the time. A lot of times there's things switching on and off. There's a lot of automatic control. There's a lot of user input in terms of turning devices off and on. And in having that dynamic interaction between all these other systems, you need to see data, and that's what the trending can do for you. All right, the next step. Transitioning away from loggers, what we basically do is we have all the same connection capabilities, all the same memory, everything that's in the logger that I've talked about so far, but we have more horsepower in the device. And when I mean horsepower, I mean sample speeds, and that allows us to get into basically away from trended into actual waveform detail. And when we get to that point where we have waveform detail, we can start now using the tool for troubleshooting. So using the word analyzer and troubleshooter in the same sentence is pretty, you know, they can swap out fairly quickly. Allows us to isolate, confirm where problems are, compare relational information between various electrical loads at the same time. And we use this for harmonic identification. I'm not going to get into too much today about what harmonics are. That could be a full half-day or 2-day session, depending on where you want to learn about harmonics, or longer if you went to university for it. Load generation issues affecting other connected devices, and again, problem solving in the moment to get yourself back up and running. This is where an analyzer and having that extra power available to you is important. Finally, in the red section, we're not going to talk too much about this today, but these are high-speed recorders. They're typically used for utility companies to be able to quickly and you know, maybe even between 2 different locations using GPS and time stamping to figure out what's happening in electrical distribution systems. They're multi-cycle, sub-cycle events, well below ½ a second, and maybe even as short as 50 nanoseconds. So very, very fast, very high-speed captures. And in the Fluke world, the faster it is, the more information, the more expensive the equipment becomes. So it really becomes a discussion between what tool best fits your job. And we start, again, over on the right-hand side between energy loggers and power quality loggers. The big difference between those two, right out of the gate, you notice that there's no display on the 1740 series. These are typically they're IP65 rated. Ingress protection 65 means it has some water and dust protection that's above traditional pieces of equipment. They actually work well in outdoor applications. You just plug it in, and you can run it if it gets wet or splashed with water, or even to the point that there's some water. It's not really typically a problem. The application here is for utility companies. They want to be able to plug these in, pull mount them, sometimes even put them inside a case, but have it available. There's to record and log data in, say, for instance, a neighborhood or an industrial neighborhood as to what's actually happening, and make sure that they're logging the power there and it makes sense with what they think is happening. The center device, the power quality analyzer. The 1770 series was just launched in October last year from Fluke. It replaced a couple of different families we had. We had a 430 series, which you may already own or be familiar with in a rental environment. The 430 is a 3-phase power quality analyzer that we sold. The new model adds some functionality to that, and there's 3 models that kind of bridge the gap between the 430 series and a 1750 series that was also recently discontinued. And the 1750 is one of those recorder type analyzer tools, so it's super powerful, well respected in the electrical utility industry space. But anyway, when we get back to this, if you have any questions about these products, GTS can help you sort through all of our models and all of the specs and all the differences, and have a logical discussion with you about what it is that you want to accomplish and what tool best fits. The top 2 models, I'm going to kind of set them aside. If you think you need one of these products, we'll have a kind of a discussion about them later offline. But they are really kind of the higher end analyzers that we have. They're traditionally used in very detailed analysis. I'll just slip over to the one on the right. The 1760 series, the interesting thing about this is that it has 8 or 9 inputs. I'm sorry, I can't remember, but those inputs are interchangeable. So I could run 8 inputs of voltage if I wanted to, or a bunch of different currents, or actually have some switching type information being recorded at the same time. So there's a lot of different functionality. A lot of programming goes into this. They're typically used in almost research on the utility side business. But I would say that the core of our business are the first 3 models you see on the left-hand side. Okay, let's talk about energy and power loggers. Because they're, what we would consider the entry level or the first step of being able to measure 3-phase, they really need to be able to be connected quickly and gather data easily. And then the software itself has to be powerful, yet easy to manage the data. We could literally put you in an ocean of data. If we're capturing a value up to 400 different parameters every half a second and you want to record for 30 days, like that's a lot of data. So the software itself is very powerful at handling these large data sets and able to filter and separate and create the ability to view and compare and generate a report. So much so that the software it's actually, I would say, even though the hardware is solid, the software functionality in our product is really awesome. And there's been a lot of time put in effort to make that functional for our customers. The devices themselves have to be easy to program. And when I say easy to program, I don't want you to get overwhelmed that you're in there programming individual things. But really, it's just a case of picking the topology. In other words, is it 3-phase delta, 3-phase Y? Is it a single phase? Like, what is the configuration? And then how often do I want to gather data? And then once I have that information, what parameters I want to measure. And once we have those 3 or 4 basic questions picked off of a selection table, you're pretty much ready to go. They have to have deep memory. Again, we'd like to have that memory have easy access and quick to download. So one of the key features that our products offer is not only memory on board, but you can put a USB memory stick on them and then send the data file to a memory stick and just use that memory stick and plug it in your computer. So it makes it easier than trying to do, have something connected to a laptop and then do a communication. It's just way easier to do it that way. There's another nice feature if you're dealing with some of our loggers that have a display is we can show you live data while you're actually still recording in the background. So if you just want to do a quick check, maybe in the morning, just make sure, yeah, everything looks good, I'm still recording, I'm happy, and then go on about your day, we have the ability to do that for you. And remote viewing options in the right application is critical. And what I mean by that is if I have, one remote in, say, the west end of town and the other on the east end of town, and one in the couple in the downtown, and I have to correlate that data and I want to see them, we have the ability to send that data through traditional either Wi-Fi or Ethernet connections onto your network, and then you can see that data remotely. Okay, let's talk about logging. Where do I actually measure energy consumption? Excuse me. So at the top of the arrow here, I'm pointing, that doesn't help you. Use my mouse. Usually as the power comes into our system, we'll want to measure what's actually happening here for kind of an overview of what all of our power is. And then you'll want to move your logger, they're portable, battery operated, move down into a load, either side of your different loads, down through into individual pieces of equipment. And this is a single line showing one. Obviously, there might be many different pieces of equipment down this line. Same thing over here. We have other transformers or panels or sub panels, and taking a look at lighting and computer loads. And ultimately, what we want to do is get a handle of how this energy is being distributed through our system, and that it makes sense. I haven't got too much load running one way and not enough another. That I'm not overloading a particular system, and I don't have unbalance happening in systems where I have a 3-phase system, but I'm pulling single-phase loads off of 1 or 2 or 3 of the phases, and they're all out of balance. Those type of situations are very quick and easy to get a handle on. The pro tip on this is log your energy consumption at each point roughly for 1 week, and know your operational limits. That's a baseline type discussion. In other words, what is actually happening from a baseline point of view. I would like to add to this pro tip and suggest that you move it around on a frequency that makes sense, and you can start to log data and trend data. And rather than leaving it in a cabinet, I suggest you pull it out of the cabinet and put it to use for you. It can sit in when I mean cabinet, I mean a tool cabinet, but it can sit in your electrical distribution system and record data for you. Go back a week later and just add that data file, maybe do a quick analysis to make sure that it didn't change from the last time you made an analysis, and just roll through and just continue to rotate it. All right. This page just talks about some customer success stories. These are two situations that happened in the US. One was an industrial park substation. The customer was measuring their system, and they found that the capacitor bank was staying on, or had been installed but stayed on, and when it wasn't being needed, it wasn't being shut off. It was creating power factor penalties for them. They were able to put in time-controlled relays and disconnect the capacitor bank at night, and saved $14,000 annually from just a poor power quality adjustment. I'll talk more a little bit about the cost of power quality, but this is just an example of, you know, how they're spending money when they didn't need to. An automotive plant somewhere near Detroit, maybe Dearborn, they saved a bunch of money. They found 3 key areas in the plant showing significant energy waste due to power quality issues. They installed some capacitors and regulatory controls and upgraded some transformers, and that had to do with Harmonics. But at the end of the day, they spent some money and then generated $50,000 of annual savings just by doing some testing with a power quality tool from Fluke. So these are not atypical. They weren't cherry picked as the best. These are typical of what our customers find. It all depends on the load or the size of their distribution system, but we can typically use an analyzer from an energy perspective and save you money that well covers off the cost of the equipment and the time and labor to make those adjustments. And then any savings just pays for any capital investment you need to make. Okay, analyzing and troubleshooting. So we've transitioned away from just the logger now back to that middle section, that 1777 series that I was talking about. And what makes the good qualities of a power quality analyzer? So first of all, power quality analyzers, they have more horsepower, as I mentioned, and because of that extra horsepower, they can show you more information. And when you have more information at your fingertips, it's important to be able to, you know, go in, analyze, find out what's happening, know what that information is, and then find out quickly, maybe even have the analyzer tell you if it's something you should be concerned about or not. The device itself can switch topologies quickly between delta and Y. Because problems are intermittent in nature, tools can transition from, you know, making instantaneous measurements to turn it into a logger and then go back to an instantaneous measurement functionality. And because they have that logger functionality built into them, they have the ability to just be left and rotated around like the previous image where, you know, infographic where we were able to move the device around and create logging for us. They should still be portable, and still have deep memory on them. And you know, having a power quality analyzer that's easy to run is one of the key features, and Fluke has put a lot of time and effort into making it easy. And the new model has these little LEDs that tell you that you got to connect it correctly, and then how to make, that's even before you start logging, so you're not logging something that's incorrect. And yeah, it's just that much easier to use than even the previous version. So let's talk about some best practices now. We shift gears out of the equipment side of things and start talking a little bit about what is good practices for troubleshooting. Traditional testing, the testing they taught us when we went to school, was, you know, start at the power supply, work your way through the little system that you're working with or whatever the case may be. And when something appears out of normal that you're not expecting, take a look at that piece of equipment and find out what it should be putting out for normal and make a decision that that might be the problem. The concern we have with power quality testing in that environment is it might take a long time to go through your distribution system to get to that point, especially on every problem you come across. So what we typically suggest you do is invert that troubleshooting and go start at the victim load. And once we're at the victim load, we want to test that load for what potential operational issues are there. So say, for instance, the motor. Is there something on the drive side of the motor that's creating an issue for us? Has it tripped the breaker because there's something mechanically causing the motor to load up? Is it an electrical problem or a mechanical problem? We should know that right away, or at least try to define it fairly quickly. Confirm the conditions that the load is expected to operate under, and that it's getting the voltage and current available to it in the right shape, the right conditions to be able to operate. And then if it isn't, consider anything upstream from that as to what could be the problem. And there's more steps to consider as a part of this whole discussion. So when we start moving back upstream, the second step we suggest you do is understand your single line drawing. In other words, what is it from that load back through the electrical system back to the source? What does that line look like for you, and what's connected? What also might be connected on branch circuits? You may have a single line drawing or a full electrical drawing available to you. The question we would raise, or the question that you would want to ask yourself, is how often is it being updated? Are the revisions being done correctly, and are they being documented correctly? Has somebody changed the transformer that they thought was like for like, but actually has different specifications and didn't change the diagram? So you're going to want to go confirm the validity once you start walking the system, which is the next thing to do. Do a walk around. You know, you'll find that when you walk around, you'll get a feel for what's happening. You might hear a motor not running correctly. You might, use a pocket thermal imager and see something that's changed in terms of that transformer's hotter, or you'll be able to see discolored wires or connections. Maybe somebody's plugging in some extension cords and they're now running something that you didn't think was even connected. Maybe there's signal wires that have been opened up and exposed to the electrical environment while they're waiting for, say, a replacement circuit board to come. It hasn't been properly grounded. Neutral bonds are in bad shape. So there's a bunch of those physical things that happen that any piece of test equipment you're going to buy from Fluke just may not be able to find this stuff. Finally, or one of the last steps I might suggest, maybe not finally, there's another one coming, but step number 4 is to interview the people involved with that problem. So if you have a manufacturing situation and you have operators that are running the equipment and they finally got around to reporting that there's a problem, you should go back and interview them and say, hey, you know what? When did this problem first present itself? What was the actual situation it was under? And how long has it been happening like this? Understand the time of day. Did it happen first thing when everybody comes in the morning? Is there other equipment running? Is there something else that they know has happened in the system? Maybe somebody's added a piece of equipment. Maybe they had a technician come in from a drive manufacturer that made some adjustments, and now that's affecting something else in the system. Having that information available as a part of your equipment maintenance log, if you're keeping logs, is a good idea and a good way to review that data while you're trying to troubleshoot. Finally, this gets back to what we suggested earlier, but collect data always. So try and get a complete picture of what's going on with energy consumption and power quality from the source to the load. Now this goes back to the traditional measuring, but what we'd like to do is find the victim load, see what's connected, and then go back later and then start to measure my data back down to that load. And having comprehensive data as a part of what you're measuring becomes very valuable. In fact, in collecting periodical power quality health at each critical load and documenting that over time can help you really narrow down what the problem is when a problem arises. Okay, you might actually be able to trend and find a problem sooner rather than later. All right, so I've thrown out a lot of terms. I just want to set the record straight here on what is power quality. There is an official standard for what is power quality. You'll see a graph from me in a couple slides from now that shows what is considered good or bad in terms of test parameters or parameters for what power quality is. And formally, it's basically quantities being measured for different types of operating conditions, and power quality itself requires measurement. That's the bottom line on that particular left-hand side of the table there. In reality, though, power quality can be very subjective. If I was, in West Texas and I'm operating a pump jack, I think it's good that I have power. It almost doesn't matter how quality the power is. As long as I have power and I can start things moving, you know, there's many times those type of applications are happy just to get power at all. But if I'm running at a hospital and my equipment has very tight tolerances and it has to work well in the sandbox with each other, having very strict power quality is very, very important. So again, it's subjective as to what is considered good or bad power quality. Generally speaking, if you have performance indicators and defined limits set up that allow your equipment to operate, and you can maintain that within your distribution system, and as long as your plant is not creating problems upstream for the utility or neighbors, then you get the job done, then your power quality really is not much of a concern. But when it does go bad, having the right tools available to find those problems and straighten it out is critical. So what is the cost of poor power quality? The actual cost of power quality comes down to the equipment losses in terms of equipment not running correctly, or, you know, in this particular image case, burning up, higher energy bills, degradation of your equipment over time, potential early failure, cost of redesigning and cost of mitigation, productivity losses, product spoilage. If the power goes out in the middle of a batch run, what does that do to your batch? And by extension, if your utility is burning coal, gas, or oil, or whatever it is, it's a carbon-based fuel. If you're wasting that energy, you're also creating unnecessary CO2. Okay. Those are some costs listed there. In the U.S., the cost is estimated to be about $200 billion annually for U.S. companies in the U.S. So if we can get a handle on it, we can potentially save that kind of money. Basically, we don't have to spend money when we don't need to. I think all of us are down for that. Okay, the value of good power quality. This page here is just a few points that you might want to jot down. If you're looking to purchase a power quality tester, these are some of the hidden advantages of being able to have a tester available to you to be able to make measurements. You know, you maybe have better uptime, predictable plant outputs, things that are maybe tougher to manage but easier to understand, and maybe potentially more appropriately affect management in terms of profitability. So how can you determine if power quality is the issue? If you have new equipment installed, you will probably be generating in some way, shape, or form new problems. They may not be big, but as you add new equipment, the problems may cascade or take you down a path of being an issue. Repeat issues that aren't going away, warranty claims on new equipment, similar equipment failures, cascading failures where you replace one part and then the next part fails and then the next part after that fails. Vendors, if you have vendors that come to you and say, hey, let's put in this product, and by the way, little asterisk, you might want to take a look at some harmonic mitigation on the equipment. That's usually an indication that they may be, you know, solving one problem but creating another through harmonics. As management's concerned, obviously billing and incurring penalties, if we can get a handle on that, again, the tools themselves can pay for any mitigations or any equipment costs to get to that point. You may have more frequent thermal issues, and equipment itself might be underperforming. So there's just an idea of what power quality might be the issue. We're not going to be here to solve every power quality problem today. In fact, there's going to be a full list of them here, but I'm noticing we're tight on time. So I do want to get through this and get to the Q&A if possible. So the utility, the basic page here is they're supposed to provide you reliable and quality power, which in our world is sine waves, sinusoidal waveforms. And the power interaction, you want to be able to have, you know, good voltage, good current, and you're not going to affect your neighbors, any resulting voltage disturbance for other equipment. Anyway, the interactions of power quality are followed up on the next couple of slides here. So again, we're not going to be able to go into all of these terms. There will be a glossary at the end of this presentation that you can make reference to, and you will get this presentation from GTS. But at the end of the day, these are some terms you may have heard of or may have come across. So voltage sags, voltage dips, brownouts, those are events where the voltage drops momentarily, causes nuisance tripping of equipment, because as a voltage drop, the load still wants current and it might overcurrent momentarily. We have voltage swells and surges that we can measure. Outages, that's pretty easy. Usually the lights go out at that point in time. Voltage distortion, that's where we get peak flat topping on the peaks of voltage waveforms. also known as clipping, but that can create big problems for harmonics and also other single phase loads like electric motors that aren't getting fully energized with the peak of the voltage. Again, transients, those are the high frequency, high voltage events. They have a tendency to roll through protection circuitry and take out electronic components. I talked earlier about a graphical way to understand voltage disturbance. Basically on this graph, if we stay inside the blue and green line in the center region here where all the happy faces are, according to the ITIC or Sabima curve, then we should be fine. This is a logarithmic graph for voltage deviation from 100%, which is our nominal voltage. 0% would be 0 volts, and 5,000 would be significantly high voltage, depending on the nominal voltage. And then this is a logarithmic graph for the speed of the event in cycles. But as the speed of the event happens, we have less tolerance for events. And to the end of the day, they consider steady state voltage plus or minus 10% of your power. So if you're nominally getting, I don't know, 120 volts, at the end of the day, they'll have plus or minus 12 volts is what they would consider okay and within the standard. Okay, they're pretty easy to understand once we see the graph, but this is how most of the disturbances are categorized when we do power quality health in our testers. Transients, I've mentioned a couple of times. Transients are actually a broader category than the high voltage, high frequency events. In fact, they go all the way down to long-term events like durations. But as we go up this graph from the bottom to the top, this is the speed of the test equipment required to get to these measurement points. And there's dollars associated with that. So at some point in time, you're going to say, yes, I'd like to see this, but I don't need to see that. And that's kind of a deciding factor on buying a piece of test equipment. Some other causes of power quality that aren't voltage related specifically are phase angle issues, harmonics, which is again a 2 or 3 day, maybe even a semester long discussion on harmonics. Unbalance is when we're taking current off of 3 phases unbalanced. Dips and swells, flicker is voltage fluctuations, frequency fluctuations. There's the glossary, and I would like to wrap up real quick here by just giving you a few takeaways from the discussion today and leave the last 5 or 6 minutes for questions and answers. So your clamp meter is your best friend. We recommend you use a clamp meter for quick checks, but know the limits of that clamp meter. When you have a 3-phase problem, you need to take 3-phase tools to that problem. From a best practices point of view, start at the victim load, walk the problem, get an understanding of what's in your distribution system, talk to your operators. Use your tools more often so you be comfortable with them when a bigger problem arises. Also use those tools to baseline normal performance, and also use them to, just use them for understanding how things interact and communicate and work within the same electrical system. Use those tools for energy efficiency testing more frequently. They typically all have that capability. The trick is trying to find time to do that, but if you let them log for you, you can get an idea that, hey, I'm having a power factor problem at 2 o'clock in the morning. Why is that happening? And is it something I should be concerned about? Am I incurring penalties because of that? What can I do to fix that? Those kind of things you can test for. And trust Fluke and GTS for your testing needs. Okay, that's it for me. Is there anything in the chat section there, Chris?
We do have a few questions. So yeah, ladies and gentlemen, we have about 5 or so minutes to take full advantage of having an expert like Ken with us today. So please use the chat feature, use the question feature to get in any and all questions that you may have. If we don't have a chance to address your specific question, either myself or one of our technical sales team will contact you directly after the end of the presentation to answer the question directly to you and get you all the information that you're looking for. Quick note, if you are looking for something product specific, price, availability, a technical question regarding your application specifically, please go to our website, globaltestsupply.com. You'll find our products, pricing, availability, data sheets, as well as our contact information, our phone number, our email, and you can connect to a live operator via chat as well. Okay, so a few questions coming in here. Okay, when it comes to power quality and power quality instrumentation, is there a suggested calibration frequency to get these testers calibrated?
That's a good question. Calibration frequency, the way I like to answer this question is it's actually more user dependent, and maybe potentially your customer dependent. So anytime, let's just take it away from power quality and just a general discussion about calibration. Calibration is, test to a primary standard. You provide traceability saying that this standard is tested to that, and it cascades up the chain of reliability in terms of how accurate the measurement is, if it's within standards or not. If I need those accurate standards to justify a decision being made for either product quality as a part of a quality program, or if I'm trying to satisfy a customer that what I'm doing or what I'm making is correct, that's definitely an application where you need to have traceable calibration. If you are questioning your results, saying, hey, I'm not sure if this is right or not, then it's probably best to get it done on a yearly basis. That's what Fluke recommends, is a yearly calibration. And I know the GTS can handle that for you. So feel free to reach out to them anytime you need calibration on any test gear, not just power quality.
Fantastic. Okay. Another question we have in from Gerald. What would you suggest as being the direct replacement for the 438?
The 438 had our motor testing, analyzing capability in the power quality tester. We have 3 models right now, 1773, 1775, and 1777. The motor testing capability, if you need that, we are actually coming out with a version that will have that in the device. And it'll probably be similar to the way we launched the 438, which was a firmware upgrade to the existing 430 series. So what I suggest is, I'm not sure the timeline. I'd have to go back to the folks and say what our timeline is for the motor drive analyzer, the MDA function, or the motor testing function, motor efficiency testing function in the 438, when we're expecting to put it in the 1770 series. But if you wanted to pick one of those 3 models now, then just do the firmware upgrade in the future. You can do that. That'll be happening. Like I said, I've heard us talking about it. I have a feeling it's probably within the next 6 months.
Okay, perfect. So a couple minutes left. Please try and get your questions in. Scott, I do see your question. That is one that we would address specifically and directly with you offline. So either myself or one of my colleagues will contact you directly to address your question. Let's see.
Hey, Chris.
Yes.
Just to go back, the 438 was an extension of the 435, and the direct replacement for the 435 is the 1775. Just to answer that part of the question, I failed to mention that part. I didn't want to make it sound like I was avoiding the answer.
No, not at all. It's a nice direct answer, direct to Gerald. Gerald, your follow-up questions, I'd be happy to address them directly with you. I know that you and I have communicated prior to the webinar as well. I'll be happy to address follow-up questions directly. We have about a minute left. Let's go with, here we go, let's see. Oh, pardon me, oh, sorry. No, sorry, actually, so the next question is, again, a little bit more application specific, which will be addressed directly offline and directly with, again, either myself or one of my colleagues. So, you know what, to respect everyone's time today, we have a little less than a minute left. So we'll go ahead and wrap up. So thank you very much, Ken, again, for the presentation. A lot of information was talked about, and thank you all for joining us. So on behalf of Global Test Supply University, thank you again. We do hope you found it informative and helpful. We are available to help you. Are the questions that you've just asked that are more application and specific to the individuals that sent them in? We are available to help you and answer those questions. We will reach out to you, and you can also go to globaltestsupply.com for anything that you need, including our contact information, phone number, email, chat, all our products, pricing, availability, technical data sheets, manuals, etc. At the end of this webinar, we have a very short survey that we'd ask you to complete. Your feedback will assist us in improving these webinars, as well as bringing you suggested topics that are of interest to you specifically. We do have upcoming webinars over the next weeks and months, so please check out the training section on globaltestsupply.com for a full schedule of upcoming events. And don't forget that as a thank you for attending today's webinar, your name will go into a draw to win $100 on your next online order. The winner will now be announced on our social media channels, so please be sure to check us out there. Once again, Ken, thank you very much for the presentation. Thanks for sticking around for some Q&A. We wish you all a great rest of the day.
You're welcome. Thank you again, everybody. Bye-bye.
Take care.